In this video we are going to analyze loop antenna using NEC simulation software. But before that, let us have a background of the loop antenna. This is a signal of length lambda meter long. This signal is applied to a wire whose length is 1 lambda meter. During the positive half cycle, the wire carries positive charge, and during the negative cycle, the same wire carries the negative charge simultaneously, because the length of the wire is equals to the signal length, that is 1 lambda meter. That's why both the positive charges and the negative charges can exist simultaneously on the same wire. Now if the same wire is bent to form a circle, then it becomes a circular loop antenna. Now you can see that the circular loop antenna, it carries positive charges and the negative charges simultaneously. This category of the antenna is called as large loop antenna. It carries positive and negative charges simultaneously along it. And now let us have another look. Now consider that the wire length is a small fraction of the entire wavelength. And if this wire is excited with same signal, then during positive half cycle it carries positive charge, and if the same wire is bent to form a loop, then the entire loop will carry similar charge. That is, here it is positive only. During negative half cycle, the wire is going to carry negative charge, and the loop which comprises of the same wire is going to carry only negative charge. Now you can see that loop during the positive half cycle, it carries only positive charges along the circumference, and if the negative cycle comes, then it carries only negative charges. Now both the charges cannot exist simultaneously because the length of the circumference is a small fraction of entire signal length. This is called as small loop antenna. Now we are going to explore this property of loop antenna with the help of simulation software. I will first simulate large loop antenna, then later on the small loop antenna will be simulated with the help of NEC software. So let's begin with the large loop antenna. Now for that, you should be ready with the radius of the loop antenna. Now let us consider that the loop antenna, it is going to resonate at 2.4 gigahertz. Now find out the wavelength at this frequency, and that wavelength should be equal to the circumference. So using this relation we can find out the radius. So the radius is coming somewhere around 19 mm. Now go to create, select circle. Now we have to draw a circle of radius almost 19 mm. For that I will drag this mouse till the radius or this x coordinate becomes 19 mm. Somewhere here it is now 19 mm. You can see actually it is in meters, 0.019 meter. Okay, so it becomes 19 mm. Now radius of the wire, let us consider is 0.5 mm. Then number of turns, you can keep it more than 50 so that you will get a smooth circle. Otherwise, if you are taking it 5, so you will get a pentagon. Now this is the loop antenna. So loop is ready. Now we have to add source, so you can add it anywhere because the shape is circular. Now source is also ready. Let us simulate it. I will simulate it for 2200 megahertz to 3000 megahertz. So now you can see that this is the reflection coefficient and SWR graph for the loop antenna. But now you can see that the reflection coefficient is very poor. So let us investigate why this is happening. So we'll go to the impedance and we'll check what is the antenna impedance. So here you can see that the antenna impedance is almost, it is 134.618 ohm, and it has got reactance of minus 33. So we'll find out a frequency where the reactance is very close to 0 or exactly 0. So you can see that the antenna, it actually has got resonated at 2.785 gigahertz because the reactance is here almost 0, but the resistance is 152.08 ohm. So what we can do for that, we can go to the main window of the NEC, go to settings, then change the characteristic impedance to 150 ohm. Now just have a look at this response of the antenna. So you can see that there is a deep fall in the reflection coefficient here, because the antenna has got resonated at this frequency, and the antenna impedance is almost 150 ohm, and the reference impedance that also is 150 ohm. That's why here you can see that the reflection coefficient is very, very small. Okay, now we'll check the radiation pattern and the current distribution at the same frequency. So it is 2785. So we'll go for far field pattern 2785. This is the 3D view of the antenna, and this is the radiation pattern. So you can see that the antenna, it is radiating normal to the plane of the loop. It is radiating upside and downside. Okay. Now our aim is to check the current behavior of the same antenna. So we'll hide the pattern. Now go to the current. So now you can see that the current is not constant. You can see that there is a variation in the current. Okay. Here. So at the feet you can see is the height of the current is very large. So the current is maximum or there, then it goes to 0, and then it increases, and then once again it goes to 0. So you can see that the current distribution, it has got 2 maximas and 2 minimas. So it's like the current distribution is exactly equals to 1 lambda, because we have designed this antenna for a particular wavelength. Okay. Now we can use another window to investigate the current behavior. So current and its phase. Okay. So here you can see that the current here, it is increasing, goes to the maximum value, then decreases and falls to 0. So if I consider that this is the positive half cycle, then and then negative half cycle, the current increases, but in the opposite direction, it reaches to the peak and then once again comes back to the 0. So you can see that the large loop antenna, it carries non-uniform current along it. Okay, now we'll go for the small loop antenna. So for that, what we can do, instead of redesigning a new antenna, we can simply change the frequency. Now for that, instead of reducing the size of the loop antenna, we can increase the wavelength of the signal. So what we will do now, we'll reduce the frequency by 10 times. So it means that the wavelength will get increased by 10 times, or you can say that the antenna size will get reduced by 10 times. So earlier it was 2200 to 3000. So we'll remove 1 0. Okay. So now you can see it is 220 to 300 megahertz. Generate. Now you can see that the reflection coefficient is 0 here, 0 dB. So reflection coefficient is very poor. Let us investigate the reason behind this. So now here you can see that the resistance of the loop antenna is less than 1, and the reactance, it is inductive and it's very large, and this is the reason the return loss or the reflection coefficient is very poor. Now we'll try to investigate the current behavior of the antenna. So we'll choose one frequency, let us 250 megahertz. Go for the 3D view. So here, so now you can see that there is no ups and downs in the current, it's constant. Reason is what? That the circumference of the loop is so small that a small fraction of the current is flowing. So either it will be entirely positive and constant or entirely negative and constant. We can investigate here phase and the current. Okay, so you can see that the phase is not changing. Okay, so current phase is same, and the magnitude, that also is uniform, and this is the nature of the small loop antenna. Now let us look at the radiation pattern of the loop antenna. Okay, so we'll go for the 3D view, multicolor. Now you can see that the radiation is omnidirectional. It's just like radiation pattern of a dipole. Okay, so the gain is almost equal to the dipole antenna only. So small loop is a poor radiator, whereas the large loop is a good radiator. That's all about the loop antenna. Thank you for watching the video.